Okay, in today's lecture, we're going to cover the section 3.3 material on applications of linear functions. So in our last section, we had introduced linear functions as functions whose graphs are straight lines. And we saw that any linear function can be expressed in the form f of x is equal to ax plus b, or mx plus b if you prefer. So in this section, we'll look at some applications of those types of functions in concepts related to business or economics, including cost, revenue, and profit, supply, and demand. So in our first example, we're told that we have a parking garage which charges $6 plus $2.50 per hour to park in. So we're supposed to find the cost function, c of x, for parking for a period of x hours. So here our cost function, which we're denoting as c of x, is given by the initial cost to enter the parking garage, which was $6, and then plus an additional $2.50 per hour. So that is $2.5 per hour, and then we're multiplying by x, the number of hours which we have parked. So the following would be the cost function for parking for a period of x hours. Now these individual parts of our cost function we can consider as what are called the fixed cost. So regardless of how long we've parked, we have a fixed amount of $6 which is being charged. And then we have this other term, the $2.5 per hour times the number of hours that we've parked, which we would call the variable cost. So we see that our cost function is linear here. It's got a y-intercept of 6, or our fixed cost, and the slope is 2.5, which is our variable cost. All right. Now in this next example, we're told that a certain type of calculator can be produced for $4 per unit, and the total cost of producing 10 calculators is $100. So in part A, we're asked to find the cost function, c of x, assuming that it's linear. So our cost function, c of x, is linear, therefore it has the form ax plus b of a general linear function. Now we're told that this calculator can be produced for $4 per unit. So that is our variable cost, which would be the slope of our line. What is the cost per calculator? So the cost of producing X calculators would be $4 per unit times the number of units produced X. So we still need to determine the value of B. That is our fixed cost. And in the problem statement, we're told that the total cost of producing 10 calculators is $100. So if we were to evaluate this function at x equals 10, that is when we're producing 10 calculators, we would have 40 plus b, and we're told that that total cost is $100. So subtracting 40 from both sides, we find that b is equal to 60. So our cost function, c of x, is then 4x plus b, which we just found to be 60. So here we would have a fixed cost of $60 and a variable cost of $4 per calculator. So in part B of this example, we are asked what are the fixed costs? Well, we've already identified them here. We would say that the fixed costs are $60. Okay. Now, in the next example, we'll consider what's called the average cost function. So let's start by defining it. So if C of x is the total cost function of producing x units or x items of some quantity, or of some object, then the average cost per item is given by the function which is denoted as C bar of x. So we have C of x but with a bar over the variable c, and it's defined as the total cost function C of x divided by the number of units we produce, and that would give us the average cost per unit or per item. And generally, as we produce more and more items, the average cost per item is decreasing in most cases. I think all cases that we would consider in our course. So in this next example, we're given a cost function, C of x is equal to 8x plus 1400, and we're asked to find the average cost of producing 100 units, 400 units, and 1,000 units. So let's start by finding our average cost function. So our average cost function, C bar of x, is defined as the cost function, C of x, divided by x. Or in this example, our cost function was 8x plus 1400, and then we're dividing by x, the number of items produced. Now, if we want, we could simplify this a little bit by splitting our fraction. So we could rewrite this as 8x over x plus 1400 over x, which leaves us with 8 plus 1400 divided by x, the number of units produced. So either of these two expressions can be used to calculate our average cost per item for the given number of items. So let's look at the average cost for the indicated values. So we were first asked what is our average cost of producing 100 units. So we're going to plug in 100 for our average cost function. So we can use either of the expressions we found before. I'm going to work with the expression given here, 8 plus 1400 over x. So here we have 8 plus 1400 divided by x, which was 100. So we have 8 plus 1400 divided by 100 is 14. And 8 plus 14 leaves us with 22. All right. So here the average cost of producing 100 units would be $22 per unit or per item. So let's see what happens as we increase the number of units produced. If we look at the average cost of producing 400 units, we plug in x equals 400 for our average cost function. And so we'll have 8 plus 1400 divided by our 400, which leaves us with 8 plus, 1400 divided by 400 is the same as 14 over 4, or 7 halves, which is 3.5. So 8 plus 3.5 gives us 11.5, and that would be our average cost, so dollars per item. So it costs $11.5 or $11.50 per unit to produce 400 units. So we see here our average cost is decreased from when we were producing 100 units. So let's consider what happens when we produce 1,000 units. So plugging in x equals 1,000 to our average cost function, we have 8 plus 1,400 divided by 1,000, which reduces to 8 plus 1,400 divided by 1,000 is 1.4. So we're left with $9.4 dollars per item or per unit for the average cost. So we're seeing here that as the number of units increases, our price per unit is decreasing. Okay. Now in our next example, we'll consider the rate of change of a linear function, which is something of the form mx plus b, which would be the slope m. So for a linear function, the slope is measuring the rate at which that function changes. So when we consider problems in linear depreciation or depreciation of assets, we could consider modeling, say, the value of a computer or some other piece of technology or an automobile, which typically decreases in value over time. Now, when we are referring to linear depreciation, we are assuming that the value of the item we're talking about at time x is given by some linear function of the form mx plus b, where the slope m will be negative since the item is depreciating in value, and the slope of that line gives us the rate of depreciation. So in this next example, we're told that a computer that costs $1,500 new is expected to be worth $750 in 3 years. So in part A, assuming that we're using linear depreciation, we want to find the depreciation function f of x for this computer. All right. So here, our general form of the depreciation function would be f of x is mx plus b. That is the general form of a linear function. And we're given a couple of pieces of information here. First, when the computer is new, so that is when x, its age, is 0, we would have a value of 1,500. Now plugging in 0 for x in this function, we have b, and we're told that that value is 1,500. So we have the value for b. Now we just need m, our rate of depreciation. So to determine that, we can look at the value of the computer after 3 years. So here, if we look at the value of our computer after x equals 3 years, we would have 3m plus b, which was 1,500, and we're told that that has to equal 750. So let's see if we can solve for m. Subtracting 1,500 from both sides of this equation, we have 3m equals negative 750. So m is negative 750 divided by 3, which would be negative 250. So our function, f of x, modeling the value of this computer over time, is given by negative 250x plus 1,500. Now, in part B of this problem, we're asked what is the domain of this function. Now, in the first section of Chapter 3, when we were talking about the domains of functions, well, they were functions that didn't have any real physical interpretation, like a dollar value. For instance, in this function, or in this example, f of x represents the value of our computer in dollars. So if we were just to look at this function without thinking of its physical interpretation, well, we might say the domain of this line is all real numbers. There's no restrictions on x. But we know here that in order for this problem and this function to make sense, well, we can't have, say, negative values for time, and we cannot have a value of our computer that is negative. So here, I'll say we must have x, which is the age of our computer, be greater than or equal to 0. When we first buy this machine, its age is 0, and we're not considering its value before then. And the value of this computer, or its price, which we found to be negative 250x plus 1500, has to be non-negative, greater than or equal to 0. So let's solve this second inequality for x. If I add 250x to both sides, I find 1500 has to be greater than or equal to 250x. So dividing both sides by 250, I find that x has to be less than or equal to 6. So combining these restrictions, we have x must be greater than or equal to 0 and less than or equal to 6. So our domain for this function would be the interval from 0 to 6, including the endpoints. We can take x equal to 0 or x equal to 6. And under the assumption of linear depreciation, when this machine is 6 years old, its value will be $0. So we wouldn't consider it after 6 years. All right. So given that, in part C, we are asked what will this computer be worth in 4 years. So to determine its value at time 4, that is after 4 years, we're going to let x be equal to 4 and substitute it into the value function that we found in part A. So we have negative 250 times x, which was 4, plus 1500. So this becomes negative 1000 plus 1500, which leaves us with $500 as the value of this computer after 4 years. And lastly, in part D, we are asked at what rate is this computer depreciating? So recall from our previous discussion that the slope of this linear depreciation function is giving the rate of depreciation. So when we look at the function that we found in part A, the slope of this line is negative 250. So here we could say the computer depreciates at a rate of $250 per year. All right. Now in our next example, we'll consider the rate of change of a cost function, which is assumed to be linear. So in economics, we refer to the rate of change of a cost function as marginal cost. So marginal throughout our course will mean a rate of change, or how rapidly something is changing. So marginal cost would be the rate of change of our cost function. So if we have a linear cost function, say cost is mx plus b, the marginal cost, which would be the rate of change, would be the slope of that line. Again, slope of a line measures the rate at which it changes. So here we could also interpret the marginal cost as the cost of producing one more item. So if we've produced, say, 50 items and we want to know how much would it cost to produce that 51st item, it's given by the marginal cost, which is the slope of our line in. So in this next example, we have a candy company which manufactures chocolate bars, and the cost to produce X chocolate bars is given by the function 3.5x plus 800. So in part A, we're asked to identify the fixed costs for this product. So recall the fixed cost is the cost that you would have if you're not producing any units. So before you start producing chocolate bars at all, what would the cost be? And we can see that here, our fixed cost would be the cost of producing no chocolate bars, which is $800 or $800. So that might represent the cost of just renting out a warehouse where this chocolate is being manufactured. Now in part B, we ask what is the marginal cost. So recall marginal cost here is the slope of our linear cost function, which in this example is 3.5. So our marginal cost is given by the slope m, which would be $3.5. So it costs $3.50 to produce each chocolate bar here. And in part C, we are asked, after producing 12 chocolate bars, what is the cost of producing one more? Well, we said that's also given by the marginal cost. Which is our slope m, which is, again, $3.5. Now, another way that we could see that is, well, we said after producing 12 chocolate bars, what's the cost of producing one more? So that would mean we're producing 13 in total. So to get the cost of that 13th chocolate bar, we could take the total cost of producing all 13 and subtract the cost of producing the first 12. Now, let's see what that gives us. So we would have the cost of producing 13 as 3.5 times 13 plus 800. And then we're subtracting the cost of producing the first 12, which would be given by 3.5 times 12 plus 800. So when we subtract these quantities, our 800 and minus 800 cancel, and we're left with 3.5 times 13 minus 3.5 times 12. So if we factor out a 3.5 from each term, we're left with 13 minus 12, or 1 times 3.5, which is that slope 3.5. So we could have also found it in this way, but if we recognize that the marginal cost represents the cost of producing one additional item, then we can get that answer immediately from our function. Now, in our next example, we'll talk about the concept of marginal revenue. So here we've just discussed marginal cost, which was the rate of change of our cost function. So similarly, the rate of change of a revenue function is referred to as the marginal revenue. So in the event that our revenue is a linear function, say something of the form mx plus b, then the marginal revenue would be the slope of the line m. And here the marginal revenue represents the revenue from selling one additional item or one additional unit. So in this next example, we're told that there is an energy company, New York State Electric, which charges each residential customer a basic fee for electricity of $19.50. And then they charge an additional 24 cents per kilowatt hour of electricity which is used. So here we are told in part A, assuming there's a total of 650,000 residential customers, we want the company's revenue function. So let's consider this. Here we would have a revenue function, which we're going to assume is linear. So let's say that our revenue, R of x, has the form mx plus b. And we want to determine, first off, the fixed revenue, say if 0 kilowatt hours are used. So the revenue that would be earned if 0 kilowatt hours are used is the value B. And let's think about what this value is equal to. So regardless of how much electricity is used, each customer is charged $19.50. And we have a total of 650,000 residential customers. So taking the price that that each of them is charged and multiplying by the number of residential customers, we have our fixed revenue, which would be 12,675,000. And we still need to find our marginal revenue. What is the slope of this line? So we can use the information that we're given about being charged 24 cents per kilowatt hour. That is the additional revenue per kilowatt hour. So that is exactly the marginal revenue that we're interested in, $0.24 per kilowatt hour. So our revenue function here, R of x, is given by 0.24, so $0.24 or 24 cents per kilowatt hour, times x, the total number of kilowatt hours used by this number of customers, plus the fixed revenue B, which was 12,675,000. So this would be our revenue function. And in part B, we're asked again, okay, well, what is our marginal revenue? That is the slope of this line. So here our marginal revenue is equal to $0.24, or 24 cents per kilowatt hour here. Now in part C, we're told to suppose that the average customer uses 1,500 kilowatt hours a month. So what would be the company's total revenue? All right. So we would have for our total revenue, if we're using 1,500 kilowatt hours, we would have our marginal revenue, 0.24, times our 1,500 kilowatt hours used, plus the 12,675,000, which leaves us with a total of 12,675,360. Okay. Now, let's see. The wording here is a little bit tricky in this problem, so let's be a little careful here. So if we are reading this that the total group of customers is using 1,500 kilowatt hours in a month, then this would be the monthly revenue that we found here. However, if we are interpreting this as each customer using this much, so we're told here, suppose the average customer uses 1,500 kilowatt hours in a month, then we want that company's monthly revenue. So in this case, the total number of kilowatt hours used would be 1,500 per customer times our number of customers, which was 650,000. So we may also want to interpret this as 1,500 kilowatt hours times the number of customers, which would give us a value of 0.24 times 1,500 times 650,000 plus the fixed revenue of 12,675,000. Okay, so this comes out to, let's see, 246,675,000. So depending on how this is interpreted, if we're assuming that each customer is using 1,500 kilowatt hours a month, the revenue function is given by the value that we've shown here. But if we're reading this as the customer base is using a total of 1,500 kilowatt hours, our total revenue function is given here. So we need to be a little bit careful about what interpretation is being applied here. So in this problem statement, I haven't stated clearly which interpretation I'm using. So we could use either approach. So let's look at another example now, making use of a profit function. So typically, a company will need to analyze its costs and the potential market for a given product to determine whether it will make a profit. So here, let's assume that we have an electronics company which is producing tablets which are sold to retailers for $200 each. And the costs of making these tablets is $1,500, where the marginal cost is $110 per tablet. Okay, so here our fixed cost was the $1,500, marginal cost is $110 per tablet. So in part A, we're asked for the linear cost function for producing X tablets. So here, C of X, since it's linear, would be of the form mx plus b, and our slope here, m, is our marginal cost, which is $110 per tablet times X, the number of tablets produced. And then we add our fixed cost, which was $1,500. So this would be our linear cost function. Now in part B, we're asked to find the revenue function, R of X, for selling X tablets. So here, the revenue would be the revenue per tablet, so how much we're selling them for each, which was $200 each, times X, the number which are produced and sold. So we've got the following. Now in part C, we're asked to find the profit function. So recall that profit is given by revenue minus cost. How much money we have coming in, our revenue, minus how much money we're spending, which is our total cost. So notationally, we would say P of X is our revenue function, which was 200x, minus our cost function, which was 110x, plus 1,500. And we're subtracting that entire cost quantity. So we have P of x is equal to 200x minus 110x leaves us with 90x minus 1500. So this would be our profit in dollars of producing and selling X tablets. Now in part D, we are asked what is the profit from producing and selling 100 tablets. So once we have our profit function, we can plug in 100 for X, and we've got 90 times 100 minus 1500 gives us 9,000 minus 1,500, or $7,500. All right. So in these next couple of examples, we'll start considering finding what is called a break-even point. So for most businesses, they need to determine if they know what their expected cost and revenue or their expected profit would be, how many units do they need to produce and sell in order to break even, so that their cost would equal their revenue, or equivalently their profit would be zero. So this point is called a break-even point. So any company can make a profit only if the revenue on a product is exceeding the cost of manufacturing it. And so the number of units where our revenue first begins to exceed cost, that is where revenue first equals the cost, or equivalently where our profit, which is revenue minus cost, is zero, is referred to as the break-even point. So let's suppose that we've got the following problem. The owners of some parking lot have determined that their weekly revenue and cost in dollars are given by the function 80x for revenue and 50x plus 2400 for cost, where x is the number of long-term parkers. So in part A, we are asked to find the break-even point. So the break-even point is found by letting cost equal to revenue. So here, our cost was 50x plus 2400. We're setting that equal to our revenue, which was given as 80x, and now we want to solve for x. So if I were to subtract 50x from both sides, I would have 2400 is equal to 30x. And so dividing both sides by 30, I have 80 is equal to x. So in order to break even, the number of long-term parkers, x, would have to be 80, or greater if I want to make a profit. Now, when we're asking for a break-even point, we're referring to a point in, say, an XY plane. So we're not just interested in the number or the value of x, but also what the cost and the revenue would be for that value of x. So here we can say if x, the number of long-term parkers, is equal to 80, then our revenue would be equal to our cost, since 80 was the point where cost is equal to revenue. So if we take x equals to 80 and we plug into either one of these functions above, we'll get the same value, which would be $6,400. So here our break-even point would be the point 80, 6,400. So we could write this as the ordered pair 80, 6,400. All right. And in part B, we are asked to find the cost, revenue, and profit when there are 60 long-term parkers. So we're going to evaluate our cost when x is equal to 60, which would be given by 50 times x, which is 60, plus 2,400. So that would be 3,000 plus 2,400, so $5,400 dollars here. The revenue, if we have 60 long-term parkers, would be 80 times 60, which gives us $4,800. And the profit, if we have 60 long-term parkers, well, profit is revenue minus cost. So we just found the revenue to be $4,800 minus the cost, which was $5,400, and that would be negative 600, measuring in dollars. So this would correspond to a loss of $600 per week if there are only 60 parkers. So here, a little interpretation there is a loss of $600 per week if there are only 60 long-term parkers. And we could have expected a loss in Part B by our work for Part A. We know we had to have at least 80 long-term parkers to break even. So if we only have 60, that's fewer than that, then we would have a loss. Now, in this next example, we'll talk about supply and demand. So here we would say that the supply and demand for an item are typically related to its price. So in particular, producers will supply a large number of some item at a high price, but if an item is high priced, consumer demand will be lower. And as the price of the item decreases, consumer demand will increase. However, for a low-cost item, producers are less willing to supply a large number of that item. So if we were to look at a function which relates supply, demand, and the price, then we could graph those functions, and we would have curves which show the quantity that will be supplied at a given price and the quantity that will be demanded at a given price. And those curves are called supply and demand curves, respectively. So in this course, when we're working with supply and demand problems, we're going to use P to denote the price and Q to denote a quantity supplied or demanded. So let's suppose that we have the following setup. We have an economist that has studied the supply and demand for aluminum siding, and they've determined that the price per unit, so here a unit for aluminum siding might represent, say, the number of square feet of siding that is being provided, and the quantity demanded, Q, are related by the following linear demand equation. So here our demand function see, it looks like my pen might be going out. Okay, so here our demand function is P is equal to 100 minus 4Q, and the supply Q of siding is related to its price P by the linear supply equation, which is given here. So the price P is equal to 0.75 Q. So in part A, we are asked to find the price if the quantity demanded is 10 units. So here we're talking about an amount demanded, so we're going to make use of our demand function, and we're given the quantity. Q will be 10 units. So setting Q equal to 10 in our demand function, we have P, the price, is 100 minus 4 times Q, which we were told is 10. So we would have 100 minus 40 leaves us with $60 per unit for our price. Now in part B, we are asked to find the quantity demanded if the price is $80. So again, in this problem, we're working with the quantity demanded, so we're going to make use of our demand function, but here we're given the price is $80. So setting price equal to 80 in our demand function, we have 80 is equal to 100 minus 4Q. We want to solve for Q. So subtracting 100 from both sides, we would have negative 20 is equal to negative 4Q. And dividing both sides by negative 4, we find that Q would be equal to 5. So the quantity demanded at a price of $80 would be 5. All right, now in part C, we're told to find the supply if the price is $50 per unit. So here we are asked about supply, so we're going to make use of our supply function, and we're told that the price is $50 per unit, so we're going to set P equal to 50 in that equation. So we would have 50 is equal to 0.75 Q. Now we can think about this, if we prefer, in terms of a decimal, or instead of a decimal, in terms of a fraction. So we have 50 is 0.75, which would be the same as 3/4 Q. So to solve for Q, we would multiply both sides by 4/3. So we end up with 200 thirds. And Q is then approximately 66.7. So the quantity demanded, or the quantity supplied at a price of $50 per unit would be about 67 units. Now in part D, we're asked to find the price if the per unit if the supply is 20 units. So here again, we're working with our supply function, and the quantity supplied is 20 units. We want the price. So using our supply function, the price is 0.75 times the quantity, where the quantity supplied was 20. So here our price is 3/4 of 20, which would be $15 per unit. Okay. So if we have functions relating supply to price, or demand to price, and we have the price of the item per unit being supplied or demanded, and we have the quantity supplied or demanded, we can answer questions about these other values. So in the last part of this section, we'll talk about when we have either a surplus of supply or a shortage of supply, and talk about an equilibrium point for supply and demand. So we would say in the event that the supply of some quantity exceeds its demand, we say there is a surplus of supply. And similarly, if the demand exceeds supply, we say there is a shortage of supply. This item is more in demand than what it can be supplied. So we would say that supply and demand are equal at a point where the supply curve is intersecting the demand curve. And that point is referred to as the equilibrium point. Now, its second coordinate, which represents price, is called the equilibrium price. And the price, which would be the price at which the same quantity will be supplied as is demanded. And the first coordinate for the equilibrium point is the quantity that would be demanded and supplied at that equilibrium price. And this is referred to as the equilibrium quantity. So in our last example, we're told that we have supply and demand functions for radial tires in dollars, which are given by the supply function S of P and the demand function D of P, respectively. So we're asked first to determine whether there is a surplus or a shortage of supply at a price of $40 per unit. All right, so let's start by finding our supply for that price. It would be given by S of P, where our price is $40 per unit. And using our function, we have 1.5 times P, which is 40. So 1.5 times 40 leaves us with 60 units, which are being supplied at that price. Now our demand at the same price would be given by the demand function D of P, where the price is equal to 40, which here is 81 minus 0.75 times P, which was 40. So this leaves us with 51 units, which are being demanded. So in this example, we ask which is greater, and here the supply is greater than the demand. So since that is the case, we say there is a surplus of supply. The demand is less than the amount being supplied. So in part B, we ask the question, we'll find the equilibrium quantity and price. So the equilibrium quantity and price, or the equilibrium point, is the point where supply is equal to demand. So setting our supply function, which was 1.5p, equal to our demand function, which was 81 minus 0.75p, we want to solve for p. So adding 0.75p to both sides, we have 2.25p is equal to 81. So to find p, we take 81 divide by 2.25, which gives us a value of 36. Now, this is our equilibrium price, and we need to find the equilibrium quantity. So if our price P is 36, to find the quantity, we can substitute this value 36 into either our supply function or our demand function, since the value of 36 is the price which makes these equal. So here, the supply function seems a little bit easier to work with. It's 1.5 times the price, which would give us a value of 54 here. So we would say the equilibrium quantity is our 54 units, and the equilibrium price is our $36 per unit. So that concludes our section 3.3 material, some applications of linear functions, and a bit of terminology relating to business, say finding equilibrium prices, quantity, an equilibrium point, a break-even point, marginal cost, revenue, profit, and so on. So these topics will be used throughout the remainder of the course, so it's a good idea to review these concepts